Okay, so before we start today, um, let's talk a little bit about the Bacon quizzes. So the Bacon quizzes are optional online quizzes that you can register for and you can take them. And the average on those Bacon quizzes can replace your lowest quiz score. So they're not just quizzes, there are tutorials, there are online tutorials that you go through that are related to topics in the class. And then when you go through the tutorials, you can take a quiz at the end of the tutorial. Okay? And so these were created by a good friend of mine who teaches organic chemistry at UCLA. And because he works right next to Hollywood, a lot of his tutorials involve organic chemistry in movies and TV shows. You know, he has several Breaking Bad references that he puts in the tutorials, for example. So many students find this to be a fun way to review some of the topics that we've learned. There's about 4 or 5 of them that go along with topics that we're learning this semester, and one of those is stereochemistry. So since we finished stereochemistry, there is now the stereochemistry Bacon quiz and tutorial available. If you're interested in doing the Bacon quizzes, you can look at the handout on Learning Suite that tells you how to register. You have to register for it on the website at UCLA. There is a small fee. It's either $5 or $6. And my friend assures me that they're not making any profits on this program, that they're just using those funds to maintain the servers and to pay student employees to be able to handle the system that they have set up there at UCLA. So it's optional, but many students have found it to be a helpful way of reviewing. The Bacon quizzes they open when we finish a topic that they're related to. So as I mentioned, the stereochemistry one is now open, and they remain open until the day before the final exam. So this will allow you to use these Bacon quizzes in one of 2 ways. Some students will take them as we go and use them as a way of reviewing for our regular exams, whereas other students will save them for the end of the semester and will do them at the end of the semester as a way of reviewing topics and getting ready for the final exam. They're generally fairly easy in my opinion, so the difficulty level is geared more towards the easier questions that we see on the exam. So they're not necessarily going to prepare you for challenge level questions, but they are going to help prepare you for some of the easier or medium level problems that you'll see. And many of the tutorials are kind of fun to go through because they point out cases where organic chemistry shows up in movies or TV shows or things like that. Okay? So if you're interested, please see Learning Suite for the document that tells you how to sign up for the quizzes. And as I mentioned, if you participate in them, your average on the Bacon quizzes can replace your lowest average on a quiz, on an in-class quiz. So it just gives you another way of making up for either a low quiz score or a time when you had an unexcused absence. All right. So today we will finish off chapter 6. We'll finish our discussion of thermodynamics. We'll talk about energy diagrams, and then we'll talk about kinetics or reaction rates. So one aspect of kinetics that we need to talk about deals with what we refer to as coupled reactions, which is a way of writing reactions that we often see when we're writing out organic reactions that occur in biochemistry. Okay? And this is a prime example. The phosphorylation of glucose at carbon 6 gives us glucose 6-phosphate. And this is the first step in the glycolysis pathway, which is a major metabolic pathway that allows our bodies to convert glucose and carbohydrate materials into energy that we can use. And so what this is showing us, this coupled reaction, has this special type of arrow here where we have a straight arrow and a curved arrow. And this is the only curved arrow you'll see. that does not show the movement of electrons. When we have a curved arrow associated with a straight arrow as a reaction arrow, that signifies a coupled reaction, and it's not showing the movement of electrons. So what it's showing is that the species on either end of the straight arrow, those are the principal reactants and products of the reaction. So what we care about, what the biochemists care about when they're thinking about glycolysis, is glucose, the original starting material, and glucose 6-phosphate, the product of that reaction, that then goes on into the second step of glycolysis. ATP is a reactant. ATP is reacting with glucose, and ADP is formed as a byproduct, but that ADP is not participating in subsequent steps of glycolysis, so we're not really worried about it. So usually what happens is the major components we're concerned about are at either end of the straight arrow, and the curved arrow is showing us a reagent, and then it's showing us a byproduct derived with the reagent. These are called coupled reactions because usually if we were to consider these two reactions separately as half reactions, it's important to note that that's not how it occurs. You don't really have two half reactions occurring. We just have one whole reaction occurring. But if we pretended that there were half reactions and we split it up, one of those half reactions would be thermodynamically unfavored, and the other one would be thermodynamically favorable, and that would provide the driving force for the unfavorable process to occur. So what we're trying to accomplish in the first step of glycolysis is to put a phosphate group on the C6OH of glucose. But right here, this equation tells us that we cannot just react glucose with monohydrogen phosphate to get glucose 6-phosphate because that is highly endothermic. This is in kilojoules. If we divide that by 4, we find that it's more than 3 kilocalories per mole endothermic. And we know that that would give us maybe a little less than 1% of the product at equilibrium. That wouldn't do. That wouldn't work for glycolysis. So we have to couple this with an energetically favorable process. And we've mentioned this a couple of times that ATP hydrolysis is energetically favorable. A lot of energy is released. More than 8 kilocalories per mole are released in ATP hydrolysis. So if we couple that with phosphorylation of glucose, we end up with an exothermic or an energetically favorable process that will give you 100% of the product and 0% of the starting material, essentially. Okay? So we don't have these two reactions occurring simultaneously. What we have is glucose colliding with ATP directly in the active site of this enzyme. And then in the course of that collision, one of the phosphates from ATP is transferred to glucose to give us the desired product and the byproduct. So it's only one reaction that's occurring, but we can split it up into two pretend half reactions to understand the energetics of the process. Doing that helps us understand why we have to burn a molecule of ATP in this process as opposed to just directly using the hydrogen phosphate. We can't directly use this because it's thermodynamically unfavored, so we have to use ATP instead. Okay? So coupled reactions, they're not really half reactions, but if we split them up into half reactions, it helps us understand the thermodynamics. In this case, it helps us understand why we need to use ATP in the process instead of using monohydrogen phosphate directly. Any questions about coupled reactions? Okay, so another concept, thermodynamic concept we need to discuss is entropy. Entropy is delta S. What is entropy measuring? So that would be the units of entropy, yeah? More qualitatively, what are we measuring when we measure entropy? Disorder, exactly. Entropy is measuring disorder. Is more disorder or less disorder thermodynamically favored? More. All right. Anybody who's a parent knows that it requires energy to maintain order. That if you do not put energy into the system, you get disorder, right? That is a law of parenting as well as thermodynamics. It's a law of doing dishes, a law of cleaning your room. Anything you do, it requires energy to maintain order, right? So the tendency to disorder is thermodynamically favored. So that means that if you have less order in the products relative to the reactants, you will have a positive value of delta S, therefore a negative value of T delta S, and that makes delta G more negative. So that's why, so positive delta S is thermodynamically favorable. Now, it just so happens that in most organic reactions, differences in delta S, or differences in entropy between reactants and products, and therefore delta S values, are usually very small. So because those values are very small, the T delta S term in this equation is usually quite small, much smaller than the delta H term. So for most organic reactions, we can say that delta H, or entropy, or enthalpy, is roughly equivalent to Gibbs free energy. Okay, so in most cases, we will equate these two terms. We'll use delta H and delta G interchangeably, because they will be equivalent or close to it in most cases. However, there are two types of reactions in which entropy is significant. Okay, the first one we'll discuss is a fragmentation. In a fragmentation, we would have one starting material A, and that would react to give us two products, B and C. Is this reaction converting one starting material into two products going to be entropically favored or disfavored? Favored. Why? We're making more particles. That's the terminology that you typically use in general chemistry. More particles in the products makes the products have higher entropy than the reactants. Okay? So in this case, when we have more products, more molecules of products than reactants, then we have an entropically favored reaction. And then in these cases, this term might be significant enough to impact delta G and make it more negative. Okay? The second type of reaction where entropy is going to be significant is a cyclization reaction. Okay? So in a cyclization, we take an acyclic molecule, usually with two functional groups, one on each end, and those functional groups react, and we end up generating a ring from an acyclic starting material. So would a cyclization be entropically favored or disfavored? Disfavored. Why? Okay. So a ring does not have we have free rotation in an acyclic compound. In a ring, we have restricted rotation. So we've restricted the freedom of the molecule to move. So we've imposed order on the molecule. And therefore, we have decreased the entropy, giving us a negative delta S, a positive value of T delta S, making delta G less negative, less favorable. So cyclizations, entropically disfavored, requires energy to impose order on the system. Fragmentations, entropically favored, you're producing more molecules, and therefore you have less order, more disorder. So these are the two types of reactions in general where we have to pay attention to changes in entropy. In other reactions, we're just going to set delta H and delta G equivalent to each other. Question? Yes?
I'm not sure if this is in scope of this class, but I've always wondered that the ATP reaction that is going to generate heat generally, right? So how does that actually get turned into like motion and kinetic energy in our muscles?
That's a great question. It's a fairly complicated process as to how it works. Sometimes it's not necessarily heat that's given off. There's an electron transport pathway, so sometimes it's stored in other ways, and then through the electron transport, there's there's a pump and so forth. It's been a long time since I took biochemistry, but it's much more complicated than we would get into in this class. So all we look at in this class are just the energetics and noting at which steps there are processes that are exothermic and that energy could be harnessed in some way. All right, so let's talk now about a way of looking at reactions, which involves energy diagrams. Okay, so an energy diagram is a graph, and we'll refer to it as a schematic representation of the changes in energy that occur as reactants are converted into products. Okay, schematic representation of energy changes that occur as reactants are converted into products. Okay. All right. So I mentioned an energy diagram as a graph. The y-axis is going to be energy, and then the x-axis we refer to as the reaction coordinate, which is a unit of time. So what we're going to do is we're going to look at changes in energy as a reaction proceeds. At time 0, we have the reactants. At the final time, we have the products. And then the graph is going to show us how the energy changes in between as we go from reactants to products. This way of looking at reactions can give us a lot of information. As you'll see by the end of the class, it can tell us how many steps the reaction has. We learned on Friday that we can have concerted reactions that have a single step. We have stepwise reactions that have multiple steps. And so we can get the information about the number of steps, relative energies of starting materials and products. We can also learn about the rate of the reaction. We can learn about whether or not there are reactive intermediates that are present. So there's a lot of info packed into an energy diagram. So let's look at a sample reaction. We're going to take a reactant AB. We're going to react AB with C minus. C minus is going to attack B. We're going to cleave this bond between A and B. And then that's going to give us BC product. And then we're going to generate A minus, a byproduct. So what type of reaction is this? We learned types of reactions on Friday. That's a substitution reaction, exactly, okay? So that's a substitution. And this is a concerted substitution. This is a one-step substitution where the bond making and the bond breaking are occurring all at once. So it's a single-step process. And we wouldn't know this just by looking at this equation, but for purposes of this analysis, we're going to assume that this is an exothermic reaction. Okay? So let's draw an energy diagram for this particular reaction. So we draw our axes, draw them like this. Y-axis is going to have energy, increasing energy on that y-axis. The x-axis, we'll call that the reaction coordinate. Remember I said that's units of time. Okay? So our energy diagram is going to look something like this. Okay? We've got reactants over here, products over here. So we would go ahead and write in AB and C minus. Those are our reactants. And then by the time we get over here, we're going to have formed BC and A minus. Okay. So a couple of important parameters that we can glean from an energy diagram. If we look at the energies, relative energies of the reactants and the products, that difference is going to be our delta H for the reaction. Okay. And that delta H is going to be essentially the same as the delta G. And then there's another difference in energy that we have, and that is the difference in energy between the reactants and the energy maximum on this, this graph. That's referred to as E sub A, or the activation energy. Okay. The activation energy is the minimum amount of energy required for the reaction to proceed. Okay? And the energy of activation is related to the reaction rate. Okay, if we have a high energy of activation, we will have a slow reaction rate. So it's inversely proportional, right? The lower the activation energy, the faster the reaction rate. Okay? And then when we look, and the energy of activation is calculated by taking the difference in energy between the maximum on our energy diagram and our reactants or starting materials. The energy maximum also has a name. It is referred to as the transition state, or TS. That is the energy maximum. Now, the transition state, because it is the highest energy species on the reaction pathway, has a very fleeting existence. Its lifetime is so short that we do not have techniques available to determine its structure. But by looking at the structures of the reactants and the products, we can infer what the structure of the transition state must be. So let's do that in this case. Let's look at the reactants and ask ourselves which bond or bonds are being broken as the reaction proceeds. Okay, the bond between A and B is being broken as the reaction proceeds. So when we reach the transition state, that bond breaking will be underway, but it will not be complete. So at the transition state, we will have a partial bond between A and B. Then we can ask ourselves which bond or bonds are being formed in the reaction. Okay, the bond between B and C. So that process is initiated as the reaction begins, and it is not complete when we reach the transition state. So we will have a partial bond between B and C. We also need to look at the charges. Are there any charged species in the starting materials? Okay, C has a charge. Does it have a charge in the product? C does not have a charge in the product, so it's going to have a partial charge at the transition state, a partial negative charge. And as we're passing through the transition state, is the magnitude of this partial charge increasing or decreasing? It's decreasing, going down from 1 to 0. Okay? Are there any species that are gaining a charge in the reaction? A is gaining a negative charge, so we need a partial negative charge on A, and that partial charge is increasing as we're proceeding along the reaction coordinate, because it's going from no charge to a -1 charge. Okay? So this is what our transition state would look like. It has partial bonds and partial charges, reflecting the bonds that are being formed and broken in that step of the reaction. So to show that we don't know the structure, that this is an inferred structure and is a transition state, we do two things. We put it in brackets. So when we see brackets, what's inside the brackets is a transition state. We also use brackets to indicate concentration, so we have to do one more thing. We put this double dagger symbol on the outside of the brackets to indicate that what's inside the brackets is a transition state. Okay? So, does anybody in the class know who came up with the theory of transition states and that double dagger notation? Yes? President Eyring's father. Yes, Henry Eyring was the developer of transition state theory and the person who devised this symbol to represent transition states. He discovered and demonstrated, he was a physical chemist. He was a very, very brilliant physical chemist, so he was very good at developing the theory of chemical reactions. So he studied transition state theory. He was the one responsible for connecting the energy of activation to the rates of reactions. And he was responsible for the theory of transition states, helping us look at transition states to try to understand their structures and therefore understand organic reactions. So many people believe that Henry Eyring was one of the most brilliant chemists to not win the Nobel Prize. So when people make lists, the Nobel Prize in chemistry is being announced on Wednesday, I believe. It's this week. This is the week that Nobel Prizes are announced. And he's no longer eligible because you have to be alive to win a Nobel Prize. But when people make lists of chemists that did not earn the Nobel Prize but were well deserving, he is oftentimes on that list. Okay, so when President Eyring talks about pulling weeds in his garden in New Jersey when he was a little kid, the reason he was living in New Jersey is that his father was a professor at Princeton. So his father was a professor at an elite Ivy League institution, very well recognized and well renowned as a chemist. But then later in his career, he and his wife decided that they wanted to move back to Utah and raise their family in Utah. So he finished his career at the University of Utah. So if you go to the University of Utah campus and you go to their chemistry building, you find their chemistry building is named the Henry Eyring Building, because Henry Eyring is still, I would believe, the most prominent and famous chemist that was ever a faculty member at the University of Utah. And so their chemistry building is not named for President Eyring, but it is named for his father. And he is responsible for this transition state theory that we're learning today. Okay? All right, are there any questions about this diagram and the information we can gain from this diagram? One thing that's important to understand about energy diagrams is that the energy of activation and the delta H for the reaction are completely independent of each other. So we can have 4 different scenarios. If we look at these 4 different energy diagrams here, we can have endothermic reactions that are slow. We hate those reactions. They only give us a small amount of product at equilibrium, and they take a long time to reach equilibrium. Slightly better would be endothermic reactions that are fast. We're only going to get a small amount of product, but at least we're going to get there quickly. Then we have exothermic reactions that are slow, negative delta H, high energy of activation. And then we have our favorite reactions, which would be exothermic reactions. They favor the products, give us a lot of products, and they have a low energy of activation, meaning we get those products rapidly. So these are the ones we like, but all 4 of these scenarios exist, and all 4 of them are possible because energy of activation and delta H are completely independent of each other. Okay? All right, so our energy diagram on the board is for a 1-step reaction. But we know that reactions do not have to be a single step. We have multi-step reactions. So how would we draw an energy diagram for a multi-step reaction? What we would do is we would consider each step separately. Okay, at the start, we would consider the steps separately, and then later on we could combine them. So let's consider our substitution reaction that we've already drawn. But let's say that it takes place in 2 steps rather than 1 step. Let's say that in step 1, we are breaking the bond between A and B. A is more electronegative than B, so that's going to be a heterolytic cleavage, giving us 2 species, A minus and B plus. And then in our second step, C minus is going to come in and react with B plus, giving us the product BC. And then just over here, we don't have to write this, but I'm just going to write A minus, indicating that A minus is carried over unchanged from the previous step. So we want to consider each step separately and draw a separate energy diagram for the 2 steps. So let's look at the first step. And the first question I'll ask is, will the first step be endothermic or exothermic? Endothermic. Why? Products are higher in energy than reactants. How do we know the products are higher in energy than the reactants? Very good. All we've done is broken a bond. And we know that breaking bonds costs us energy. So we know that the products will be higher in energy. Anytime that all you do is break bonds, you know that that step is going to have to be endothermic. So our energy diagram will look like this, with the products higher in energy than the reactants. So here we have AB, our products. I'll draw them off to the side here a little bit. A minus and B plus. The difference in energy between reactants and products is delta H. And the delta H in this case is positive because the products are higher in energy than the reactants. And then the difference in energy between the reactants and the transition state is the energy of activation. What is our transition state going to look like? A half bond between A and B, okay? Are there going to be any charges? Okay, so we have no charges in the reactants. We have charges on each of our products. So we're going to need a partial negative charge on A and a partial positive charge on B. Okay, then we put it in brackets and put our double dagger symbol on. Okay. Any questions about the energy diagram for step 1? Yes, please.
Not exactly about step 1, but can't you just combine these into the same graph?
We could, but we want to take it step by step. We have to have something to combine first before we combine them. So we're going to analyze them step by step first, and then we can put them together. So let's look at the second step. Will the second step of the reaction be endothermic or exothermic? Exothermic. Why? All we're doing is forming a bond. We know that forming bonds releases energy. So we know that the products of step 2 are going to have to be lower in energy than the reactants of step 2. So our energy diagram, let's just make this a little bit higher so it's easier to draw. Our energy diagram will look like this. Let's go ahead and write our axes on. So B plus and C, A minus isn't participating in step 2, so I'm going to leave A minus off of the graph for step 2. These are the reactants we have in step 2. The product we have is BC. So we see we have a negative delta H, and then, whoops, not there. Sorry about that. Our activation energy, the way I've drawn it here, our activation energy is relatively small. Okay. What will the transition state look like? Okay, partial bond between B and C. Okay. As we're proceeding through the transition state, is this partial bond getting stronger or weaker? It's actually getting stronger. What about the partial bond in this transition state? Weaker. So this, I'm going to make this partial bond a little stronger, so hopefully it can be seen better on the camera. So that's one difference between these two transition states, is this partial bond is increasing in strength as we pass through the transition state. This one is decreasing. And then we have our partial charges, partial positive on B, partial negative on C. Are these charges increasing or decreasing at the transition state? Those are decreasing, okay? All right. Any questions about this energy diagram? Yes? Yes. Because you have to put energy into the system to get these are going to have to collide, and they're going to have to collide in the right orientation in order for the bond to form. And it's going to require energy to get them to collide in that proper orientation. So that's the reason why we have a transition state that's actually higher in energy than the reactive intermediate. Okay, so as has been mentioned, we can combine these two steps together to generate a single energy diagram for the entire reaction. And there's a few things we learn by doing that. We see that we have two energy maxima, meaning there are two transition states. And the number of transition states corresponds directly to the number of steps in the reaction. So if you look at an energy diagram and you see two maxima, that tells you that it's a two-step reaction. If you see only one, then it tells you that it's a single-step reaction. Okay? We see that each individual step has a delta H, and there is an overall delta H for the reaction. In this case, it's exothermic. We didn't know that at the beginning, but when we look at this, we see that indeed this reaction overall is exothermic. We see that each step has an energy of activation. The energy of activation of step 1 is much higher than step 2. So that means that step 1 is the rate determining step. We see that term right here. The step with the highest energy, higher energy of activation, and therefore the slowest step of the process, is the rate determining step. The overall rate of the reaction will depend exclusively on the rate of the rate determining step. We also see that there is a local energy minimum in between our two maxima, and that is our reactive intermediate. We see that right here, reactive intermediate. B plus is a reactive intermediate because it's formed in step 1, but then it's not one of the final products of the reaction because it gets consumed in step 2. So reactive intermediates are higher in energy than reactants or products, but lower in energy than transition states. So they're high energy species, but not as high in energy as transition states, which means that in many cases they can be detected, they can be observed. They usually have longer lifetimes than transition states, but their lifetime is not super long. They do get consumed rapidly in most cases. Okay? Any questions about this diagram and the information you can gain from this diagram? Okay, then let's get our eye clickers out. We have a step in a reaction. It's the second step of this particular reaction. But we're only looking at this one step. Is this step endothermic or exothermic? Go ahead and talk to your neighbors and come up with an answer. All right, let's maybe take a couple more seconds, come up with our final answers. Okay, any more? All right, that looks like all of our answers for today. All right, looks like there was some debate on whether this was endothermic or exothermic. Nobody picked neither, so that's good. If you chose endothermic, please raise your hand and tell me why. Yes, please. Okay, very good. So in this step, we are breaking a bond. We're not forming any new bonds. We know that breaking bonds requires energy, so this has to be endothermic, right? Energy is being absorbed. It requires energy. Any questions? Okay, so understanding and interpreting energy diagrams is an important skill for Chapter 6, so make sure that you practice this. This is the sort of thing that the TAs will go over in more detail in their recitations this week. But now let's talk more about kinetics. Kinetics are the study of reaction rates, and we've already alluded to kinetics a little bit today. We've talked about how energy of activation is directly related to reaction rate. We also have a way to study kinetics known as a rate equation, where we can express the rate of the reaction as an equation. It equals a constant times the concentration of the reactants. So the rate constant is going to be a large number for a fast reaction, a small number for a slow reaction. That rate constant is determined experimentally for reactions. But it's only the concentrations of the reactants that participate in the rate determining step that appear in the rate equation. So let's look at our first example, which is up on the top board now, our one-step reaction. And let's write a rate equation for that reaction. The rate is going to equal a constant times what? Concentrations of what? AB. Anything else? And C minus, okay? Both of our reactants are participating in the rate determining step, so both of them must appear in the rate equation. Now, we didn't write them in, but there are exponents to each of these terms. We have a 1 exponent on each of these terms, and that's what we'll see most of the time. If we were to see a 2, that would mean that 2 molecules of that species are involved in the rate determining step. But in this reaction, it's 1 molecule of each, so we have 1s here. So we have an order for a reaction. The order of the reaction is the sum of the exponents of the concentration terms that appear. So what is the order of this particular rate equation? It's 2, or second order. Okay? So we say that this is a second order rate equation, or a second order reaction. We can also give the order with respect to the individual reactants. So we can say that it is first order in AB, and it's first order in C minus. Okay, it's first order in each of the reactants, second order overall. Any questions? So if we double the concentration of AB, what would happen to the rate of this reaction? It would double. If we cut the concentration of C minus in half, what would happen to the rate? It would be cut in half, exactly. And that's because it's first order in each of those components. All right, let's look at our second one. The one that's on the middle board here. What concentration term or terms would appear in our rate equation? Just AB. AB is the only species that is participating in the rate determining step. So we would say this reaction is first order. It's first order overall, and it's first order in AB. It's zero order in C minus, because we don't see C minus here. So what would happen to the rate of this reaction if we increase the concentration of C minus by 10? Nothing at all, okay? And so we could determine experimentally if this rate equation were accurate by changing the concentration of C, and if nothing happened to the rate, we would know that this equation is correct, okay? And chemists do those kinds of experiments all the time, all right? Any questions about rate equations? Yes, please. For a coupled reaction, so because that coupled reaction is a single step and a single reaction, you would just put both reactants on the concentration of both reactants. So in that case, it would be both ATP and glucose that would be involved because it is a single step process. Okay, good question. All right, so let's talk about how we can increase the rate of the reaction. This is how we can measure it, determine it, see how it changes. How would we increase the rate of the reaction? Okay, we can increase the temperature. Why does increasing the temperature increase the rate of a reaction? It is, but what's happening physically when we increase the temperature? Okay, the molecules are moving faster, and so they're more likely to collide. Exactly. We increase the frequency of the collisions by increasing temperature. We have to have collisions in order for reactions to occur. So that's how increasing temperature increases reaction rate. This is not universal, but it's kind of a guideline. For every 10 degrees Celsius increase in temperature, the reaction rates roughly double in the majority of organic chemistry reactions. That's just a guideline, okay? What else can we increase to increase reaction rates? Concentration of reactants in the rate determining step, right? Only the reactants that participate in the rate determining step, okay? For a similar reason, if you have more reactants in the same volume, you're going to have increased collisions and therefore faster reactions. None of this has any impact on thermodynamics. We're not changing the relationships in energy between the reactants and the products, but we are getting to that equilibrium faster by increasing temperature or concentration. There's a third way that we can increase reaction rates, and that is to use a catalyst. Okay? A catalyst is a substance that increases the rate of a reaction and is recovered unchanged. At the end of the reaction, we can recover a catalyst and we can reuse it. Okay? So here's a reaction that requires a catalyst. We're going to react hydrogen with ethylene to make ethane. This is thermodynamically favored, but I've never seen it happen anywhere on Earth without a catalyst. Very high activation energy without a catalyst. You add a palladium catalyst. Usually it's on a carbon support, so it's called palladium carbon. And now that reaction can occur. And what's happening? That catalyst is enabling a lower energy pathway. So it is changing the structure of the transition state, making that transition state lower in energy, and therefore lowering the activation energy and speeding up the reaction. So in terms of an energy diagram, what's happening is shown here. It's important to note that a catalyst is not changing the relationship in energy between products and reactants. This particular example is endothermic. Those products are higher in energy than reactants. But you're going to get to those products faster with a catalyst than you would without a catalyst. You have a lower energy transition state and therefore a lower activation energy and a faster reaction. What are catalysts called in nature or in biological systems? They are called enzymes, okay? So biological catalysts are enzymes. Here's a cartoon-style graphic showing us how an enzyme works. I usually don't like cartoons. I usually like the structural drawings, skeletal drawings, but enzymes are too big to draw in that fashion. So here's our enzyme. It's a protein in the vast majority of cases. Substrate is the biochemistry word for starting material or reactants. And that substrate will bind to the active site using non-covalent forces, hydrogen bonds, van der Waals forces, these sorts of things. It'll form an enzyme substrate complex. And then, so that substrate will change. This is not the same as the substrate, even though it looks that way, but it's in between the structure of the substrate and the product. So this corresponds to the transition state in a reaction. But the enzyme can stabilize that transition state through these non-covalent forces, lowering its energy, allowing the reaction to proceed fast. And then at the end of the reaction, the products are released, the enzyme is recovered unchanged, and it can catalyze another reaction, okay? So enzyme is a catalyst, and a substrate is just reactant, and then the enzyme substrate complex is analogous to the transition state. Questions? All right. Well, that's it for chapter 6, and we will start chapter 7, alkyl halides and substitution reactions, on Wednesday.